We have this recovery from the little ice age, and we're going to see that more later after the break when we talk about glaciers. You're going to see that in spades with glaciers. Third is the sun. It is hilarious watching climate alarmists try to deny that the sun has anything to do with climate. It's a fascinating spectacle. Now, so over the last second half of the century, where this warming can't be explained, remember we have all this mystery warming that can't be explained, the sun was far stronger in the second half than in the first half, as measured by sunspot activity, which is a decent way of measuring it. Here's the actual 11-year sunspots. You see those spikes coming up. It goes in the cycle. I put a trailing average on it so you can sort of see what the size of it. But you can see it's much stronger here than here. 73, a month in the second half of the century, 48 spots a month in the first half. Much more active in this period. Now, there's a lot of reasons why this may not be enough activity to explain all the warming, but there's also some theories about how this might get amplified via cosmic rays and cloud cover, which I won't get into. But the sun was stronger in the second half than the first half. Might be one reason why the temperatures were warmer in the second half than the first half. Another is ocean cycles. This is the fourth thing that in the models very clearly admit the ocean cycles. This is the Pacific Decadal Oscillation. There's also an Atlantic AMO, Atlantic Oscillation. The ocean cycles are complicated. I'm going to grossly make it way easy, but basically the circulation patterns of the ocean change every 20 or 30 years. And the oceans can go through cycles of sometimes burying heat from the surface and sometimes sort of unearthing heat up to the surface. And they go through these cool and warm cycles. And if you have just overlaid it, and I didn't make up this, this is from a different data set. I just looked up when were the boundaries considered the Pacific Decadal Oscillation, cool and warm cycles. I overlaid them in this chart, and voila, look. When PO is cool, it's down, PO warm, up, PO cool, down, PO warm, or down or flat, PO warm, up. Now we're just turned into a cool cycle, and it was headed down. The ocean cycles make a tremendous difference. And particularly in this period, because this is the period they say that can't be explained by nature. And this period is, because it's so steep, is very much in the influence of that warm cycle. I did an experiment. A couple of people, I think they're here tonight, actually sent me their cuts at doing this. And I just did my own. It didn't take me very long. But what I said was, let's just try something. Let's take a sine wave. And it's just a regular sine wave, and the period of that sine wave is about the length of the ocean cycles, okay? It's hard, it's not exact, but it's about the length of the ocean cycles. And then let's just take a linear trend, okay? Just getting a little warmer every year, a linear trend. It's actually 0.4 of a degree per century, okay? And let's combine those two, because if this was really global warming, you wouldn't see a linear trend. What you'd see is flat and then up or curving up. A linear trend would not be what you would see with CO2 global warming. It's what you would see, say, from a natural recovery from the little ice age. So I just added those two curves. That's it in orange. And in 15 minutes of work, these two curves don't have any physical meaning, so I don't think I've somehow explained the world, because this doesn't explain everything. It doesn't say physically why it's there. But I did show that the temperature history, even this unexplainable period since 1970, can be easily explained as a sine wave, some regular cycle like the Pacific Decadal Oscillation, plus a regular trend. And just to finish off the analysis, I didn't have full time to throw in the AMO, the Atlantic Oscillation. I just overlaid the Pacific Oscillation onto a linear trend. So instead of the sine wave, I took the actual data for the Pacific Oscillation, overlaid it onto a linear trend, and that's the orange. It's a little high in here, but generally it does a pretty good job of explaining temperature. So folks always say that skeptics don't ever explain the warming. They don't offer an alternative. Well, I just offered you 4. Okay, 4 alternatives to the warming. I think, and I'm not saying that CO2 is not part of it. I think all 5 of them are a part of it. But for all 5 of them to be part of it, it means that CO2 has warmed the Earth maybe 1/10 of a degree or less over the last, and it's been one of the drivers, not the only driver over the last 50 years. So is warming due to man CO2? Likely some, but not most. So we just talked about that the world has warmed some, but there's not really a good smoking gun that CO2 is the primary driver of that warming. It could well be one of those drivers, probably is one of those drivers, but there's also a number of other drivers that are probably important too. And all the mix of those meaning that CO2 probably hasn't had, the primary impact over the last century. So now we're going to talk about the models. And we remember this chart. The only thing I've changed is I have to give myself some room down here in negative land for a reason you'll see in a minute. But here's the forecast. Same things we showed. Remember, this is atmospheric CO2. This is the area that we'd expect to be by the end of the century. This is where we are now. This is where we started pre-industrial. Remember, we talked about feedback. There's one thing I didn't tell you about feedback, okay? And I'm going to tell it to you now, and I'll use an analogy for you. If I'm found on my kitchen floor with a kitchen knife in my back and my wife's standing there, the police are probably going to think of her first as a suspect. Sorry, honey. So don't think about it. And even if she's not standing there, you know, when a spouse dies, the police know that 95 or whatever % of the time, the other spouse did it. And so they have a way of sort of saying, what's the most likely thing to happen here? When a natural scientist looks at a natural process, they're going to assume it's driven by negative feedback, particularly when that process has been stable for hundreds of millions, billions of years. So we have a climate that's been stable all this time. And Michael Mann, remember, even told you and says that the temperature was unbelievably stable in a dead range of like 0.1 degree for the last 1,000 years, was temperature over the last 1,000 years, and in that hockey stick. But despite that, climate is a car balanced on the very top of this mountain where the slightest nudge will push it over. It makes no sense. It defies any kind of logic or any kind of gut feeling that a natural science would reach a process. Long-term stable processes are not balanced on the top of the mountain waiting to be tipped over. Or else they would have already been tipped over. A gust of wind, an earthquake, a volcano, another car passing by, an animal bumping into it. Something would have sent that car down the mountain millions of years ago if it was really so precarious. The same is true with climate. So the natural scientist tends to assume there's negative feedback. Now that doesn't mean that it can't be positive feedback. You can have stable processes with positive feedback. But remember, a lot of guys like Al Gore and Joe Romm and even James Hansen, head of NASA's GISS, they're not just saying positive feedback, they're saying tipping point. That means a feedback factor greater than 1, if you know what I'm talking about on that. That means runaway process. That means temperature shooting to infinity with small changes in CO2. And so, but natural processes just don't tend to sit here for that. Now, I haven't disproved it yet. There are natural processes that operate like positive feedback at tipping point. One is nuclear fission. So atomic bombs are an exception. But I think you could also realize from that example that once it's gone off, it's not sort of sitting there anymore. It's gone. And that's what happens in a positive feedback system. If you remember, they mentioned a couple positive feedbacks. I'm only going to go into a couple because I have a better way of disproving it. One is that we put more moisture in the air, and moisture is a greenhouse gas. Well, all the models assume that the relative humidity as we warm stays constant. Relative humidity is how much is the water carrying compared to its carrying capacity, and that carrying capacity changes as it gets warmer. So if you say the relative humidity is constant, as the air gets warmer, that means more and more moisture is in the air. So the models all assume constant relative humidity. But as we've warmed in the last 50, 60 years, relative humidity at most levels of the atmosphere has actually fallen off. So the models are actually wrong here. They're overestimating the water impact based on this. The other thing is methane, and you really should go on and search because you'll see that this is the hot talking point in the catastrophist camp right now. And they're all saying that you go look this up. We are accelerating methane right now. Methane is running away. Methane is out of control. Methane is growing faster than ever. You will find those articles. I think I saw one in the Republic the other day. And this is the methane in the atmosphere over the last 20, 30 years. Actually, it's even steeper here. Methane in the atmosphere is actually a diminishing curve. It's actually the growth of methane in the atmosphere, this is the concentration, is actually slowing down. And nobody really knows why. This is a mystery, by the way, so I'm not going to say that this is proof one way or the other. But methane has actually been slowing down over the last 50 years. And so it's hard to say that we're having the methane positive feedback. But I got a better way to talk about positive feedback. Because remember, we kind of have an experiment in place. Because we have been measuring temperatures for a while, and actually CO2 has already risen. It's risen from pre-industrial 260, 270 back in here to, you know, the current 385, 389. And so we can actually, these curves, since they weren't going forward,